Some applications of the angular momentum conservation law we talked about in the last couple of videos. All right, let's just begin with a very quick review. Angular momentum, like translational momentum, is not always conserved, but it's conserved as long as you're looking at a system where there is no non-zero external net torque, or you could say that the external torque on the system must be zero. It's similar to what we said translationally. As long as your net force was zero, you don't see an acceleration of the system's center of mass, and therefore its momentum would be conserved. Formula was I times omega, and the units were kilogram meter squared per second. So I want to talk about whether or not it's possible for a particle to have angular momentum. We know that an extended body can have it if it's rotating, but what about a particle? Well, let's start with the formula, I omega. We need to know really if a particle can have a rotational inertia, I, and an angular velocity, omega. Starting from a rotational inertia, I, is that possible for a particle? It is, and it was one of the first inertias we introduced back when we had our unit on rotation. It is given by mr squared, which really makes a lot of sense, right? Because if you're a particle rotating in a circle, all of your mass is located at a distance of r from the axis of rotation. So this is the same as the inertia of a ring or a hoop or a loop, those synonyms, where in the same way all of the mass is located at the edge of the circle. How about omega? Can a particle have angular velocity? It can, and we also have a relationship to connect angular velocity omega back to translational velocity v, which was v equals r omega, or solving it for omega, it's v over r. So we know how to find these quantities for a particle, both I and omega. Let's try to find its momentum. From that formula, once again, I omega, we're going to color code it this time to keep track of what happens. I'm going to first replace I with the I of a particle, which is again mr squared. And I'm going to continue with my strategy of using brackets to denote that I've substituted something into a formula. So mr squared omega, and then we also said that omega was v over r. Subbing that in, v over r. You're going to lose one r in the numerator and in the denominator, but one does remain in the numerator. And we end up with this result, R cross MV. Now it's very, very important that you don't mistake this cross, this X, for a simple multiplication sign. That is not what I mean here. This is the cross product, a vector multiplication strategy that we haven't talked about. So all you need to know is that it's the same idea as when we used to do torque, for instance, except I didn't give it to you as a cross product. I just told you how to do it using trigonometry. So a cross product means using the sine of the angle between the quantities. So in the case of this R cross MV, it's the angle between R and the translational momentum. So now we have two different formulas, both of which can be used to find the angular momentum of a particle. Here they are. And once again, the bottom, you'll notice that I have replaced cross with sine theta, same thing. And for whatever it's worth, if this had instead been a dot, and there's a lot of formulas that have a dot product, then you would have just done cosine theta. Dot means cosine, cross means sine. momentum conservation for orbiting bodies to a real example. Halley's Comet, and it's pronounced Halley's Comet, by the way. This is one of those things that people mispronounce because there was a band and a guy named Bill Haley in his comets. But it's really Halley's Comet. It's named after a guy who discovered its periodicity. And speaking of that, its period is 75 years, give or take. 75.3 on the slide. It was last seen from Earth on February the 9th of 1986, which means it won't be visible again until the year 2061, in the middle of the summer. So mark your calendars. Its closest approach, which I already said was called perihelion, when it's closest to the Sun, it's 0.586 AUs away. An AU is an astronomical unit, and it's defined as the mean distance between the Earth and the Sun. So this is, I think, a really fascinating result. Even though Halley's Comet goes really, really far away from the Sun at aphelion, that's the farthest distance, at its closest approach here, it's significantly closer to the Sun than the Earth ever is, right? Only about 59% of the distance from the Sun to the Earth. I'm also going to give you its velocity at this moment, its closest approach, and it's 60,000 meters per second. Then in about half of its period, 37, 38 years, it's on the other side of its orbit, or aphelion, and there it's going to have to be moving the slowest. And at that moment, its velocity is about 1,000 meters per second. You now have enough information to solve for this. At its next aphelion, its farthest distance from the Sun, which occurs about 8.5 years from today, what will be the distance between the Sun and Halley's Comet? Go ahead and pause the video and see if you can use angular momentum conservation to calculate this distance. Solutions. So starting from the angular momentum conservation, we're going to say L at perihelion is L at aphelion, or the angular momentum is the same in both locations. I'm also going to specify that we're going to model the comet as a particle, which makes complete sense because it is negligibly small compared to the enormous distance between the Sun and the comet. So starting from my formula, the new formula for angular momentum of a particle, RmV sine theta is equal to RmV sine theta. M is on both sides. We can drop that out. That would be the mass of Halley's Comet, so that's the same. And sine of theta would be 90, sine of 90 degrees. So remember, that's going to be the angle between R, which is the line from the Sun to the comet, and P, the momentum. P is always in the same direction as velocity, and so that's a 90-degree angle, or very close to a 90-degree angle. So sine of 90 is 1. We can drop out sine of theta. And this simplifies nicely. We just end up with RV is equal to RV. Plugging in the numbers I gave earlier for velocity and R, or the distance, I'm going to keep my R value, my distance value, in astronomical units, which is fine. It's just that my answer will also come out in AUs, and you get 35 AUs.